Greetings, everyone. Thanks for attending our webinar today on building envelope inspection. I'm Scott Weiland with Innovative Engineering. I'm the speaker for today. This webinar was actually rescheduled from July 29th due to some technical difficulties, and so we also postponed it until 1 p.m. to better accommodate our West Coast visitors. And I want to welcome everybody from Seattle to Jamaica today. We're going to be covering building envelope inspection, more specifically facade inspection. However, before I get started, just a few housekeeping items. I'll be playing a video with some audio toward the beginning of my presentation. And if for some reason you have trouble with that, I apologize. You might try refreshing your connection or a different browser, or just bear with us until we get through the two short videos. If you have questions, we're going to hold those until the end, if that's okay with you. We're going to have a chat box that you should be able to find by navigating the lower portion of your screen, I believe. We're also an AIA CES provider, and we're providing certificates of completion at the beginning, or at the end of this course. It's said that a piece of building facade falls off of a building about once every 3 weeks. And unfortunately, it takes death, destruction to encourage local building authorities and major facility owners to institute their own facade ordinances, typically requiring inspection of a facade about once every 5 years, close up. And because facade is just a part of the overall building envelope, and the facade is impacted by the building envelope, including the roofing, it's important to look at the entire envelope. So today I'm going to be showing a couple of videos. There's lots of examples of this, and you actually don't have to watch the news very long to see examples in New York City, for example, of pieces of facade falling off of buildings and injuring or killing people. Of course, those are the ones you hear about. There's a lot of them that occur that you never hear about because it didn't make the news. We're going to talk about the behavior of different building materials when subjected to the environment. Much like a parking structure, your building envelope is completely exposed to the environment. It sees the full temperature swings, moisture, groundwater, rain, snow, ice, ultraviolet radiation, and all of these work to degrade the envelope of your building. They also cause movements of materials, and it's differential movement of materials that also causes further degradation of the building envelope and the facade. We're also going to talk about inspection of both the facade and roofing. We're going to be taking a look at some common issues that we see in roofing and building facades. And then we're going to touch real lightly on reporting. Reports are kind of a benchmark. It's a permanent documentation of what you did, what you saw, what needs to be done. And a lot of ASTM standards on doing inspections don't include a cost estimate, but we feel as though an estimate not accompanying a report is a mistake because you're going to find defects and you need to plan for repair. And the only way to really plan properly is to know what the cost is going to be. Once again, I'm Scott Weiland with Innovative Engineering. My company has been in business for 25 years. I've spent 40 years plus in both the design and the construction business, and have kind of developed an expertise in building envelope inspection. I'm a level 1 SUAS, which essentially is a drone, stands for Unmanned Aerial System Thermographer. Authored a number of articles on building facade inspection and spoke at a number of conventions about everything having to do with building envelopes and inspection. I split my time these days between our Atlanta office and Seattle office, and so welcome those of you who are here today from Seattle. My passion, not only am I a lifelong learner and trying to gain experience and knowledge of all things buildings, but my passion is to share my experience and knowledge with owners and property managers to try to demonstrate to them how spending pennies on engineering can save dollars in construction and maintenance. Just so we're on the same page, a building envelope is just that, it's an envelope. It covers all 6 sides of the building. You can see the blue line on the left covers the roof, covers the facade or the walls, also covers across the bottom, the foundations, the slab on grade. And so moisture can penetrate the building really from any direction. Facades, which are the source of facade ordinances, are shown on the right-hand side there. And of course, they're just one element of the building envelope. And it's the reason why you need to look at the entire building envelope, because it has a direct impact on the facade. This is a photograph taken in 2015. Cleveland is one of the more recent cities to adopt a facade ordinance. And a father and 4 boys were attending a Cleveland Cavaliers game and had just left their vehicle 10 minutes earlier, and a large portion of facade, a cornice actually 30 feet long, fell 17 stories to this car here. And you can see that if there weren't anybody killed, they certainly would have been injured. It was blamed on high winds, but of course it wasn't anything higher than what you would normally design a building for. And the source of it was basically old age and lack of inspection. This is a video that was captured on security camera. Unfortunately, most failures like this are not usually caught on high definition, 4K video. But this will give you an idea of a fairly recent 2017 facade inspection. Here, this is in Atlanta. You'll notice on the left-hand side, a pedestrian approaching this building. Had they been a few minutes earlier, things might not have turned out so well. And this facade fell down and damaged a couple vehicles. And I'm gonna play this video clip.
In the last hour, we got this security camera video of a building facade crashing to the ground. You can see right there a driver swerving to avoid it. Channel 2's Tom Regan is live on Pryor Street in downtown Atlanta. Tom, people there think heavy rain caused the facade to come down.
Dave, the sidewalk here on Pryor Street remains closed. You can see the debris piled up here from the fallen facade. It broke off from way up there early this morning. And a short time ago, Atlanta police kindly provided us with dramatic street security camera video of what happened.
There's just been so much water, it just caved in.
Karen King suspects the torrential rains this week weakened the cornice molding that has adorned her family's building since the 1980s. Early Friday morning, a section of the ornamental siding broke off and crashed onto the sidewalk.
The building is in very good shape. It's just being pummeled by day after day of rain. It just crashed, it rotted and crashed down.
Just heard a loud noise. Alan Taylor was working across the street when the molding ripped off the side of the building and fell to the ground.
There's a direct hit right on the sidewalk. It looks like water damage on the plywood top under the copper ledge.
Another construction worker told me part of the falling facade damaged a couple of vehicles in front of the building.
There was a SUV and a truck sitting there when it come crashing down, and it landed on top of the SUV.
Many witnesses said it's remarkable the large structure didn't hit anyone walking by.
We are feel very lucky that nobody was hurt. We are calling structural engineers, we're calling emergency crews to come clean up the mess, and then hopefully the city of Atlanta will allow us to open the front of the building so our clients can get inside.
The city engineer told me the damaged facade didn't affect any other area of the building, so it was allowed to remain open. Live in downtown Atlanta, Tom Regan, Channel 2 Action News.
You could tell from the video that cornice was probably added sometime later in the building's life. And as that one gentleman mentioned, water got into the cornice and rotted the supports. And they blamed it on heavy rain, but I've never been in heavy rain enough to see it bring down the facade of a building. Also, in the same year, downtown Atlanta made the national news with having streets closed due to facade panels coming off a 34-story building. It was a pretty high-profile case that we worked on and got called in to investigate, had the attention of the mayor's office while we were working on it. And so the next video you're going to see is a video of some of these panels coming off the building. You can see why they closed the streets with a little bit of wind. There was no real control over where those panels were going to wind up. It was blamed on high winds again. And it just happened to be Tropical Depression Irma passing through town. And however, the wind speeds were only recorded to be about 40 miles per hour. Atlanta, like most parts of the country, the design wind speed is 90 miles per hour. So even though the wind aggravated the panels, had there been facade inspection done, this deficiency would have been easily uncovered, and this event would have been averted. We did investigate this and discovered that these panels were held on by uncoated screws that corroded easily. And then there was also some metal clips that suffered fatigue damage just from the wind flutter on these panels. As I mentioned, it kind of takes death or destruction to institute local authorities to create facade ordinances. There's currently 12 of them in the country now, and of course an ordinance is law. Typically requires inspection of facades at least every 5 years. You can notice here that most of these locations are in the Northeast, which is the Rust Belt. Reason for that is they have the most number of freeze-thaw cycles, also the highest temperature swings. Across the South and up the West, the temperature swing is a lot less, and the climates, pardon me, are a lot more mild. Just because you do not have a facade ordinance doesn't mean you're exempt from making sure that the exterior of your building is safe. This is the International Property Maintenance Code. It's called a permissive code. In other words, it has to be adopted by your local building jurisdiction in order to become law. But it requires you to maintain your facade in a structural sound and sanitary manner so as not to pose a threat to public health, safety, and welfare. Most cities that I'm aware of have adopted this. Larger cities such as Seattle and Atlanta have their own versions but are very similar and have the same requirement when it comes to facade maintenance. We expect a lot from our building envelopes. It's what keeps the outside out and the inside in. This is actually a veterans hospital in Gainesville, Florida, and protects us from the environment, moisture, temperature, and of course also provides an aesthetically pleasing exterior skin of the building. There's a number of sources of deficiencies to the building envelope. Natural aging is probably the #1 item. That's aging of, as Joe Stiebrick would say, dead dinosaur juice. It's aging of sealants and roofing and waterproofing. Ultraviolet radiation tends to break it down. It tries to break it down into its original constituents. And so, elevated temperatures, prolonged sunlight exposure will speed up the degradation of waterproofing materials. Water may be the #1 ingredient for a healthy landscape. but it's the #1 enemy of a building envelope. You can get leakage through the roof, walls, windows, joints, can cause rot, corrosion, mold, provides a breeding ground for insects, staining, spalling, which we'll cover in a future slide, but has to do with either moisture, freezing and expanding and breaking off pieces of the facade, as well as building up vapor pressure and things of that nature. And we mentioned earlier the movement of materials. All materials move, all building materials. They move thermally, they expand and contract when the temperature changes. They also expand due to moisture. Some don't, but a lot of building materials do. Elastic deformation, basically all building materials deform elastically. And what that means is as you load up something, it deflects. And then if you take that load away, it returns to its original shape. Creep is another item that most building materials are subjected to. Creep is the plastic or permanent deformation of materials due to sustained dead loads. They don't have to be very high. They're a function of what the melting temperature is. So it's a function of material properties. It's a function of the temperature, the amount of stress, and the time over which a material is loaded. With building materials, creep is pretty predominant in wood and concrete. For airplanes, for example, steel can actually be a creep issue. The fan turbine blades in an engine can get heated up and creep and hit the cowling. And so, all materials are not, there's no materials really exempt from creep. I digress a little bit, apologize for that. The other sources of damage, not quite as likely, is impact damage from vehicles. You've probably seen that on the news, especially recently here at Piedmont Hospital, and lightning damage, which is not as common, but it does happen. We've investigated a number of situations that have had lightning damage. This is a building, or a picture of a building here, and you can see the darkest blue is the most exposed areas of the building to moisture, followed by the lighter blue, and then you see blue here at the base of the building as well. The base of the building can be subjected to splashing water from rain. It can also be subjected to capillary action of groundwater coming up into the facade material. Concrete, for example, if it was covered with waterproofing, capillary action could cause the moisture to travel 6 miles. So capillary action is a pretty strong natural phenomena. Over here on the left, you can see water intrusion accounts for 70% of all construction litigation. And the damage functions, of course, are water. As we mentioned, it can damage interior of property, cause rot, corrosion, buckling of materials, mold, provide a source for termites and insects. Heat accelerates degradation of material. So when materials are degrading or rusting, it's a chemical reaction. And if you go back to your science days, heat actually accelerates chemical reactions, and it's no different with building degradation. Ultraviolet radiation, as I mentioned earlier, UV light will work to try to convert waterproofing and roofing type materials back to their original constituents. And so it's the reason why we have to pick out materials that are ultraviolet resistant, or cover those materials, say with a roofing ballast, to protect it from ultraviolet radiation. Older buildings, around the top of the building, you'd see a cornice here. And one of the examples there, that cornice failure, the cornice actually pushes water out away from the building and reduces the amount of this dark blue area. A couple principles of building science. One is 90% of water intrusion problems occur within 1% of the total building exterior or envelope. And that usually occurs at terminations and transitions of waterproofing material. In other words, waterproofing material transitioning from one material to another. I tried to circle on the right here the number of areas that would have transitions and terminations. I could put a lot more circles on here, it'd be all circles, but you know, between the parapet and the roofing, you've got here windows in the adjacent wall. There's a three-dimensional thing going on here, and all of the adjacent waterproofing materials need to be, you know, tied together. The other principle in building science is 99% of water intrusion problems are attributable to human error, including detailing, specifications, or installation, not necessarily the materials or system failures. When you don't detail or construct your waterproofing transitions properly, it leads to problems. When you don't detail it properly, the only option for a contractor is either ask a question through an RFI or use more sealant. And sealant may last as short as 2 years, depending on the type of sealant, if it was the proper material, and the exposure to ultraviolet radiation. We talked about transitions. Oftentimes on a set of drawings, you will see a lot of 2D details. Some of these are reused from project to project. However, it doesn't necessarily tell the whole story. You can tell on the picture in the right there that really you had to draw a 3D detail to figure out what exactly is going on there between, you know, 1, 2, 3 of these surfaces. And 3D details take a lot longer to draw, but if you don't draw them, the contractor's got a guess as to what to do. And like I said, he answers that guess by just putting a lot of sealant on. There's 3 basic types of exterior walls or facades of a building. Many years ago, we used what's called a mass wall. The picture on the left here is a brick. You can see concrete, you can see masonry. That's a mass wall. So all 3 of these walls have control layers that prevent water from getting into the building, as well as air, vapor, and temperature. A mass wall, the idea behind a mass wall is as the exterior of the wall gets wet, the water slowly migrates toward the interior of the building, but it's able to be evaporated before it reaches the inside. And that's basically how a mass wall works. However, a mass wall assumes that it's solid. And you can see here, on the left, we cut a hole probably for a new opening on a building recently. And you can see the voids in the CMU, the voids between the brick and the CMU. And obviously that's not solid as it should be, and won't necessarily work the way it's intended to. The limitation of mass walls is they're also load-bearing walls. And if you get up to about 16 stories, your wall thickness is about 6 feet thick. And you kind of reach the practical limit on the height of a building because as you get taller, of course, the walls just got to get thicker and thicker. So to answer this, with the creation of cast iron, ductile iron, steel, and later reinforced concrete, the wall was separated from the skeleton of the building. And that's a barrier wall system. So the barrier wall, they separated the structure from the control layers here for water, air, vapor, and thermal, and into one essentially system here with no secondary drainage. And while it sounds good, it rarely works. We had situations early on with EFS in this country where EFS, you know, it's like the plague now. No one wants EFS, but it was not a drained system, whereas modern EFS is drained and a lot more successful these days. So to get past this barrier wall system and basically one line of failure, we've been using for the last decade or so a cavity wall system. This cavity wall system has brick or stone cladding, and that tends to shed water away from your building system. Behind that is an airspace with a drainage layer, and any water that happens to get in through the cladding will drain to the bottom of the wall and out through weeps. That's followed by your other control layers, your thermal, as you can see, insulation here, and then your air and your vapor, all outside of the structure. We mentioned differential movement of materials. Thermal expansion contraction coefficients are different for different building materials. And you can see here that if you had an aluminum curtain wall system, for example, it's going to expand and contract about 4 times that of brick, about 5.5 times that of concrete. And so you have to adjust or allow for that differential movement. And there's no stopping that movement. It's going to move. And if you try to resist it, you're going to break something. Similarly, moisture, a lot of building materials expand and contract subject to moisture. CMU in concrete, for example, is the largest it will ever be after it's cast. And as the water in the concrete and CMU hydrates, and as it evaporates, the CMU will shrink. Now this is reversible. As it gets wet, it expands again. Brick, by contrast, is fired in a kiln, fires off all the water. It's as small as it's ever going to be when it comes out of the kiln. And for the rest of its life, it's absorbing moisture and expanding. So while you got CMU shrinking most of its life, the brick is expanding. Obviously, if you tie the two together, you're going to have problems. This is an example of thermal expansion. This is a long parapet wall with not the first joint in it. You can't see the elevation here, but you got to take my word for it. 30 or 40 years ago, not much was known about the differential movements of building materials due to moisture and thermal expansion. And generally on brick, you would have an expansion joint vertically about every 25 feet. You would have a relief angle at every floor, and that would allow the brick to expand and contract. In this particular case, this long parapet that's exposed to extreme temperature changes on both sides of the wall expanded, and that expansion was restrained by the returning end walls here, and it caused the wall to buckle. And how that buckled was there was a through-wall flashing here, you can see in the center picture, that allowed this wall to kind of lean over a little bit and allowed for that buckling to occur and that expansion. And you can see the picture on the right here, that expansion was like 3 to 4 inches. Similarly, this picture here, I think was taken in Shreveport, Louisiana. You can see some lines on the ends of the wall here. Those lines are actually not joints. Those lines are cables from the lightning protection system. And so this wall here doesn't have the first joint. Generally, you'd have joints every 25 feet, the either side of windows. Like I say, it doesn't have the first joint. And so if you took a close-up of this corner, you'd see this crack here on the corner. That's Mother Nature's hinge at the end of this wall. You would normally see about 2 feet back from one corner of this wall a vertical expansion joint that would prevent this from happening. And so what's happening here is the brick is expanding, and while it expands, it's being restrained by this return wall, and it just can't handle the stresses, and it breaks. And because you don't have a joint, you really can't control where that breakage occurs. This is an example of moisture expansion contraction, possibly a little bit of thermal differential. This wall here is a 34-story building. It's a center courtyard that is not accessible. And so it's perfectly protected from people getting in here. But what happened was, is this CMU inner wall was tied to the brick exterior wall with turn brick. And the brick, of course, is expanding and the concrete is shrinking, and it's just fighting each other, and eventually it can't take that load. And so this wall wound up being connected at the top and the bottom, and it was pretty much free floating in between. Because of the turn brick, it couldn't deflect inward, so it deflected outward. And here's an example of one of the windows. You can see the large joint here, and that's, people have tried to fill it with sealant. There's a practical limit to how big a joint can be, and that's represented here. We were able to stick a borescope into one of these holes, and the picture on the right is actually, a remote camera. So the picture on the right is taken with a remote camera, and you can see this turn brick has broken away. You can see that where it broke out from here, the depression, and you can see where the two walls have separated. And the wall bowed out about 4 or 5 inches at the mid height. And like I said, there's no stopping this. So if you don't allow for it, you're going to have problems. This is an example of moisture damage. On the left-hand side, you'll see spalling of the face brick. There's about 3 different possible mechanisms here. You can see the capstone has sealant, which is always a bad idea, because sealant has a finite life and degrades due to ultraviolet radiation, and will allow water to penetrate into this wall. And the water in that wall, a number of things can happen. One, you can get water, moisture saturated in this brick, and as that wall heats up, exposed to the sun, it can turn to vapor, and the vapor causes pressure. It's only about 4 psi, but there again, there's no stopping it. The other thing that can happen is this moisture can be subject to freeze thaw. Freezing water expands about 9%, no stopping it. The other phenomena is through a process of osmosis, and that is water carrying salts that are common in building materials such as lime and parge coats and things of that nature. And it carries salts through this material, and then you get evaporation from within the material, which causes sub-efflorescence. In other words, the water, just like on the exterior of a building, the water evaporates, it leaves this white powder, this crystalline powder, and as that powder is crystallizing, it's expanding, and that too can break off the face shell of this brick. The picture on the right is also caused by water damage. If you zoom in here, I'll try to do that here. If you zoom in, you can see there's a drip edge here, and that drip edge somehow got bent down and is not working the way a drip edge is supposed to work. And what can happen is through tension and capillary action, water can actually travel, gets to this point, travel back underneath this overhanging cornice piece, saturate the concrete, and due to freeze thaw can spall the concrete, which you can see here. And similarly, this piece that we have in our hand is a piece that's spalled off at this location. Another failure mechanism is corrosion. You take ferrous metal, moisture, and oxygen, you're going to have rust. And rust expands about 6 times the original parent volume of the material. So there's no stopping it. And so what happens here is the expanding rust popped off the mortar that was, thin layer of mortar that was covering the edge of this relief angle. And then it also popped off a piece of the brick. Similarly, in concrete, this is actually a screen wall around a cooling tower. It likely didn't have enough concrete cover or protection of the rebar, and this rebar corroded altogether, and delamination occurred, which is where they all corrode together and they all pop off the face of the concrete together. And so you've got exposed reinforcing steel here. We talked about elastic deformation and creep. Elastic deformation and creep are subject to how much load is applied. And buildings, of course, will shrink due to elastic deformation and creep. And so if you don't separate the facade panels from the building and allow for that differential movement, you'll be transferring some of that building load onto the facade. That's what happened here on the left with a piece of limestone panel. Of course, it caused it to buckle. Had too tight a joint here, probably had mortar in it. You need to allow for that differential movement. On the right is a project we did in California, and facade inspection we did in California. And these are terracotta panels. And this building, there was no expansion or no contraction allowed at the top of these panels between it and the structure. And the structure settled down under these panels. Of course, you know, they're not designed to take that load, and they broke at the base. You probably have all seen this on the news. Unfortunately, recently here in Atlanta, we had a situation in a hospital where someone drove into the emergency room. This is when someone mistakes the gas pedal for the brake or drive for reverse. And we've looked at a number of these, even including buildings driving through precast, stone panels, tilt-up walls. The picture on the right is damage at a loading dock. If you look closely here at the right, you'll see a dock seal. It's hard to make out other than the color of the material there. That's a dock seal where a truck backs up to a loading dock and seals off around the opening in the back of the truck. Well, you can tell that the driver wasn't allowed very much room to try to navigate this, and it's no surprise that someone has hit that wall there. We mentioned lightning strikes. Lightning is it's the #1 cause of fatalities due to weather. It used to be about 3,300 deaths per year back in 1940. Now it's only between about 40 and 100 annually. A lot of that's due to improved building codes and also education of people, you know, not to stand next to a tree in a lightning storm. It also causes billions of dollars in property damage. What happens is lightning tends to be attracted to the corners of building. Of course, it's looking for the path of least resistance, so it's looking for steel. And basically what happens is the lightning temperature is about 50,000 degrees, or about 5 times hotter than the sun. And whatever moisture is in the building pieces or piping or anything that has water in it, it superheats to steam and explodes. And so what happened here was, this is actually in Chattanooga, Tennessee, lightning struck the corner of the building, this cornice here, and exploded, fell to the sidewalk below. You can see on the right-hand side a close-up of what was left after that piece blew out of the corner. And you can see one of our rope access technicians standing on top of what's left of the cornice. So you get a pretty good idea how big a piece that was that fell. And thank goodness no one was hurt or killed. Facade inspection procedure starts with typically the building engineer. They have the most knowledge and experience of the building. They know where the defects are. They know when the additions happened. Most importantly, they typically know where the drawings are. And so we try to find drawings to see additions, how the facade and roof is constructed. This picture here is actually in Reno, Nevada. This building engineer was very helpful. So we look for previous reports, specs, if you can get them, shop drawings, if you can get them. Most VA hospitals, that happens to be a veterans hospital here on the left, they usually keep a pretty good set of drawings. And then we follow this up by doing a general visual inspection, either with binoculars or a drone, and followed up by a detailed hands-on assessment of the facade of the building. And then we classify deficiencies. If it's unsafe condition, we report it immediately with a proposed fix, or at least short-term fix, and then generate a pretty thorough report and construction estimate. I mentioned doing a visual survey first. After you talk to your building engineer and you've uncovered the known defects, areas of concern, you can either look at the building with binoculars and a telephoto lens camera, or a drone. Drone usage has increased a lot lately, but whether you're using a drone or binoculars with a remote telephoto lens, if you're looking up at a building that has people in it, they get concerned. And so that's what the reason for this picture on the right is, to remind me to tell you that no matter how often we check in with the police and tell them what we're doing, we always seem to get a visit. And so this is Stephen Morgan, one of our senior engineers, explaining to the police officer what it is we're doing and why we're appearing in people's windows. Close-up detailed inspection. Once you've done a visual and identified what the deficiencies are, this gentleman on the left is in San Francisco. This is a mass wall concrete system, and he's doing sounding with a hammer. We also have a rotary hammer that goes a lot quicker, that you'll see in an upcoming slide. On the right-hand side is St. Albans, New York. That's Trey Thomas, another one of our senior engineers, industrial rope access certified. He's actually looking in a joint with a bore scope to look at the supports for these panels to make sure that they're in good condition. On the left here is a gentleman on a boom lift. You can tell it's cold out the way that they're dressed. It's probably in the Northeast somewhere. You can see snow in the background. But what he's doing is he drilled a hole in a mortar joint. He's looking behind the brick with a bore scope. And on the right-hand side is a photograph taken from a bore scope. And this is a brick tie, and you can see that it's in perfect condition. It's not corroded at all. Pushing, pulling, tugging is how you look at something close up and tactily. Sealants is another area that you can push and probe on them, and you can check the adhesiveness between the sealant and the adjacent substrate. You can tell if the sealant has started to revert back to its original constituents. It'll be kind of gooey, or you just visually you can see if it's all cracked up and dried out. On the right is a rotary hammer we use for sounding that I mentioned earlier. The old method of sounding was called a chain drag, and you would take a broom-shaped looking device with a bunch of chains on it and drag it horizontally along a slab. The nice thing about this rotary hammer is you can speed up that process, and you can look at not only downhand conditions, but you can look at vertical walls and overhead ceilings, and cover 100% of the area in a very short amount of time. Lastly, thermal inspection. Our drone that we use to do the visual also has a thermal camera on it, and we're able to look for anomalies. Generally, you're looking for areas that are wet, but in this particular case, we were able to see that there's actually cool air leaking out of the building at this joint here. Facade inspection would not be complete without looking at the roof. Good quality roof, including the parapet coping, is a key to having a successful facade life. And this is a market share graph, and basically you can see built-up roofing, which at one time dominated the market, no longer does. In the 1970s, with the increased cost of oil, it opened the door to other systems, polymer modified systems, such as modified bitumen, EPDM, PVC, and TPO. You can see these days is very popular. Modified bitumen is probably the most similar to a built-up roof. It comes in 3-foot rolls. It is 3 times thicker than the other systems, the EPDM, PVC, and TPO. And for that reason, it's a lot more puncture resistant. The other systems would include things like metal roofing and foam roofs, spray foam roofs. This is the cost per square foot. This is out of RS means, and so these costs need to be adjusted depending on where you are in the country. If you are re-roofing, you got to add about 50% to this cost. But you can see the built-up roofing now is pretty expensive, followed by modified bitumen, EPDM. EPDM with a ballast is a pretty economical system. Like I said, these EPDM, PVC, TPO is about 1/3 the thickness of modified bitumen. EPDM is similar to inner tube material. If you add ballast to it, however, you've got to have more structure because the ballast typically weighs 12 to 15 pounds per square foot, and the structure has to accommodate that. So it's something that you would probably want to consider when the building is new, maybe not as in a re-roof situation. PVC and TPO, both plastic. TPO has only been around since about the 1990s. The formulation's continually being improved. ASTM standards are changing, seems like every couple of years on that product. And so it's the least proven, but it does seem to be, from the previous slide, the most popular. A common issue to all roofing systems is ponding. I see this more often than not. Ponding is defined as standing water that's in place longer than 48 hours after a rain event or snow. And roofing is really not designed to be waterproof. Sounds kind of weird, but it's really designed to shed water and to be water resistant. Water actually degrades asphalt. It degrades polymeric materials. Often standing water will void a manufacturer's warranty. If it freezes, it'll dislodge the aggregate on a roof. And so it's important to have good drainage on your roof. And if you have a situation like this, you need to do something about it. Built-up roofing, as I mentioned, it was actually invented in the 1840s. And like I said, in the 70s, it kind of fell out of favor just due to cost of oil. The number 1 and number 2 causes of failure here are blistering and splits. Blistering is when water penetrates the roofing and gets underneath it and gets heated up during the day, and the water gets converted into a vapor, and a vapor expands the volume about 1,500 times, and there's no stopping it. And so you can see a lot of blisters on this roof. It kind of looks like a lunar landing practice field, and you can tell this roof has exceeded its life expectancy. On the right-hand side is a common thing. This is actually slippage, which is not as predominant as blistering and splits, but this is slippage of the flashing here, which cause splits that will allow water to enter into the facade system. Modified bitumen, as I mentioned, it's 3 times thicker than EPDM and the other plastic systems. Comes in 3-foot wide rolls. It's a 2-ply system. You can get aggregate surface to protect it from UV exposure. By far, the number 1 mode of failure on this is just poor workmanship and defective lap seams. And lap seams, of course, can be tested with a probe. If you're not seeing the oozing of asphaltic material out from this edge about 1/4 of an inch, you don't really have a good seal. And in this particular case, it didn't even take a probe. Just a finger could lift up that seam. And of course, that's where water can get into the system. EPDM, its number 1 cause of failure is lap seam failure. In the process of manufacturing EPDM roofing, generally it comes in 10-foot rolls. When it's manufactured, it's kind of squished down as it's rolled, so it's stretched out, and you need to let it sit about 30 minutes or so after you unroll it before you try to seam it together, because what happens is it tries to shrink back to its original shape, and you get what's called peel type stresses. Essentially pulls the seams apart. Like I said, that's the most form of failure. You put an aggregate on this, and you got a pretty good system. PVC, also developed in the 70s along with EPDM. It's thin like EPDM, about 1/3 of mod bit roof. Also comes in about 10-foot rolls. One advantage to it is the seams are thermally welded. They're said to be stronger than the material itself. Number one failure mode is embrittlement followed by puncture, and due to long-term exposure to high temperatures will cause embrittlement, and you step on this less than about 50 to 60 degrees Fahrenheit, and you will break the surface. You can see here where some of the plasticizer on the left has washed away, exposing the scrim or the fabric reinforcing of this, and it's essentially degraded. PVC is actually an excellent product if you have kitchen exhaust, say exposed to like animal grease, things of that nature. TPO, as I mentioned, was developed in the 90s. It's the newest material. As far as I can tell, it's still being improved upon. There are some situations where this material has performed well for 20 years, but there's still a lot of ongoing studies being done for this. Premature aging due to heat, it has been the number one problem, followed by seam failures. The seam failures seem to occur through improperly welded seams. There was no real standard on temperature and things of that nature on welding the seams. Like I said, it's the newest roofing material. Here you can see the picture on the left. The plasticizer has actually washed away and exposed the scrim or fabric. The roof inspection procedure, much like the facade inspection, you want to meet with a building engineer, find out where all of the hidden defects are. This again is in Reno, Nevada. See the mountains in the background there. It's recommended that you inspect your roof about twice a year, early spring after the winter and late fall but before the winter. After you have a severe weather, hailstorm or hurricane, and or if you have work done on your roof. It's a good idea to go up and walk the roof and look for defects. There again, you want to see what documents they have on the roof, maybe when it was last inspected, maybe the specifications for the roofing material. You're going to conduct a visual survey, includes a moisture survey with thermography, either a handheld thermal camera or a drone, preferably. You'll report the condition and estimate the cost of repairs. Typically, if more than about 25% of the roof has got to be repaired, that's usually what kicks you into replacing the whole entire roof. Moisture intrusion into the facade is typically caused by coping or roof flashing at the perimeter. You can do visual inspections of the underside of your roofing as well as the top side of your roofing. It also helps when someone can help show you where the leaks are, just to see if you're paying attention. You don't have to know how to spell in order to find a roof leak. Infrared drone technology. You can actually look at a roof with handheld thermal cameras. Problem with that is you get reflections off of other surfaces, and it's hard to discern maybe where the water damage is. The best time to thermally inspect a roof is after dusk. You let the heat of the day warm up any wet material below the roof, the wet insulation, And at dusk, when it starts cooling off, the dry insulation will cool off much faster than the wet insulation. And so the wet insulation will show up red hot, as you'll see in a second here. It does require a daylight waiver from the FAA, which we happen to have one. They're not terribly difficult to get. You got to give them a procedure, on a safety procedure really on how you're going to conduct nighttime operations. It is safer than walking the roof in the evening, safer to fly it than it is to walk. This particular drone here, you can tell is just taken off. Typically you'll fly it higher overhead so you can pick up, if not all the roof, a significant portion of it. This is an example of some drone images that we've taken. The visual, so our drone has a visual camera and a thermal camera. And so the image on the left here, they call it an RGB, red, green, blue image. It's basically a visual image, and you can see dirt that's deposited itself here, which means that you probably get some water ponding in this area. On the right-hand side, you'll see the red hot areas. Those are areas that obviously have water. Now with thermography, what you're measuring is surface temperature. And so you're identifying what are called anomalies. You are identifying areas that potentially have water. And so you need to check that. A non-destructive means is a impedance meter that checks the electronic signal between a couple of electrodes. A more destructive means, a little bit more accurate, is a pin probe. You stick a couple pins, through the roofing, and it'll measure the electrical resistance between those two probes. And you need to just plug a couple little holes. The most accurate thing to do is take a roofing core. It provides you with the most information. It provides you with the makeup of the roof. If it's been re-roofed, you can determine if the roofing contains asbestos. And then you can take a sample in a Ziploc bag back to the lab and weigh it, cook it in the microwave, weigh it again, and you can figure out what the moisture content was. If your roof is still under warranty, I would suggest you have the roofer out there along with the inspector to make whatever patches are necessary. Reporting. The ASTM standard for periodic inspection of building facades is another ASTM standard on inspecting roofs for wet insulation. They contain some information about what to include in a report. Estimate is not one of those items, but we feel like a report without an estimate is not really of much value. And our reports generally talk about the original construction, what alterations have been made, renovations, additions, things of that nature, the overall general condition of the roof or the facade, findings and recommendations by deficiency level, detailed description of what the different structural systems, facade waterproofing systems are. We'll document on building elevations and plans where the deficiencies are. As I mentioned, we'll estimate the cost of repair. And then we'll, as far as categorizing facade deficiencies, the ASTM E2270, you can classify deficiencies by unsafe condition. An unsafe condition is an imminent threat to persons or property and immediately needs to be brought to the attention of the owner or local jurisdiction as required with a repair or remedial options. Requires repair and stabilization. That's an issue that could become unsafe if it's not addressed before the next inspection. Ordinary maintenance is just that. It's a deficiency. It's not a life-threatening situation, but it needs to be taken care of during the next scheduled maintenance. So we talked about the importance of facade inspections, why they're important, why it's important to look at the whole building envelope and not just the facade. We looked at the behavior of building materials, expansion, contraction, differential movement, things of that nature. The inspection process for both facades and roofing, and then we just lightly touched on reporting. And with that, I will thank you for your attention, and we're going to attempt to open the floor up to questions. And Bijan Garagozlu, who's my right-hand man here, is going to be reading the chat box and feeding me with any questions that you have. This is my contact information. I've got both my Atlanta office and Seattle office there. I'm actually going to be in Seattle next Wednesday, and be glad to come see you if you would like me to. And then there's my cell phone. You can pretty much reach me anywhere with that number. So Bijan, do we have any questions?
The one we got so far was from Stacy. She asked if we were going to be recording and sharing the webinar with everyone. And I got back to her already and told her that we would.
So it did get recorded?
Yes.
Okay, good. All right. Well, so we're a little bit new at this technology, so I hope it all went well. We're learning like everybody else. You know, we're accustomed to giving in-person presentations, and so this whole webinar business, we've been slowly figuring it all out. So I hope you enjoyed the presentation. Like I said, if you think of any questions, feel free to email me, give me a call. Would love to hear from you. Anything else?
Everyone's saying thank you.
Well, you're quite welcome. I usually probably go overboard being an engineer, you know, with data and that, but I like to provide as much useful information as I possibly can.
All right. Well, I think we are good then.
All right. Thank you all for attending. Stay in touch. Thank you again. Bye-bye.